Hey everyone. So last time we did the Deutsch algorithm. This time we're gonna do the Deutsch-Jozsa algorithm. I really hope I'm pronouncing that right. Um, the idea is we're going to generalize from just one bit input to our mystery function to an n bit input, sorry, rather. What that means is we're gonna have, instead of just a zero or one, we're gonna have n zeros or ones as our input to the function. Let's kind of refresh the circuit from last time that we did. Let me get my pen back. There it is. Right. So we had this and we had that as the 2-qubit register. That was the input to the circuit originally. They both went through a Hadamard gate, and then they went through a controlled unitary, where the unitary was acted sort of like a C naught gate, except instead of flipping on 0 or 1, it flipped on whether our mystery function f of 0 or f of 1, um, f of x, whatever it was, f of x gave a 0 or a 1. F of x, rather. F of x gave a 0 or gave a 1. And based on that, the control bit here, it would flip or not flip these bits down here. One more Hadamard gate, measurement. And that was that. That's how we got the output. And after just one query to this box, we knew immediately whether we had a constant or a balanced function there. With the HOSA addition to our algorithm, we're going to be able to do, with the same circuit, in fact, we're going to be able to put a more interesting input through here, which is just going to be the same zero, but with many, many more bits here. N bits, in fact, as many as you like. And we'll still only have to do one query to the circuit, which is the amazing part. How do we do that? Well, let's kind of just go through a proof slash workings of the algorithm again with more inputs. So this time we're going to have 0 of n rather than just 0. This stays the same. Putting this through a Hadamard gate, we're going to get something that sort of looks like this. Times more of these. Times more of these. And so on and so on. And so we're going to have to kind of foil these sorts of things here, right? This will just be a 0, 1 minus. Now at this stage, we have our controlled unitary knot. You have F, there it is. And we'd like to use this mess as the control for our gate here. And what's going to happen, if you'll recall from the last lecture, is if f of x is 0, it will not flip. It will make this 1, and the sign will remain the same. If in fact f of x equals 1, it will raise this to the power of 1 and leave it as -1, which will flip the sign. And we're going to take this and put this through another Hadamard gate after. And I think I'd like to actually take this here now and get us used to this nomenclature. We've seen the Hadamard gate enough times now to kind of pick up on a pattern here. The Hadamard gate doesn't do much to a 0. Well, it takes a 0 and it puts it into a linear superposition of a 0 and a +1. And a -1, it puts into a position of a 0 and a -1. So if we abstract this pattern out, we're looking at just kind of sign flips on this. X, Y. If they're both zeros, this is raised to the power of 0 and there's no sign flips. If this is a 0, this is a 1, then there's a sign flip, sign flip, sign flip, right? You can kind of see the pattern there. That's just kind of abstracting this out. what a Hadamard gate would do to these kinds of things. So now we see, whoops, we see this is going to be stacked with this to represent the Hadamard gate. Here it is. Y rather. Because that's just how many FOIL terms we're going to have. Where X is the original bit, that's going to be transformed into Y, right? Whoops. Now, after all these gates here, we're going to have a state that looks something like this. Where X of Y is this, shorthand for this. This is the modulo plus 2 operator. This caret is the and. Oops, Y2. Okay. Now, this again is an abstraction of the pattern of the Hadamard gate. And I'm actually going to leave it as an exercise to the watcher to fill in the exact algebra and details as to why it's going to give us this. But remember, it's the same circuit as the Deutsch algorithm. So this circuit is going to be exactly the same as the one we saw in the Deutsch algorithm. And I want you to kind of go through the algebra of the sign flips and figure out why this expression, this Boolean expression, makes sense to express how the signs are going to be flipped the way they are, depending on when his bit is transformed into another bit by a Hadamard gate. Essentially, remember, we have these sum of sums and this product of sums, and we're going to have, let's say, a 0 go to a 1, or a 0 go to a 0, or a 1 go to, that kind of thing. Based on that transformation, that's determining the sign flip, this Boolean expression here. I want that to be left as an exercise to the watcher here. Now we have this expression here, and I want you to notice that if f of x is a constant function, it can actually come right out here outside the summation. Ignore y for now, and I want to concentrate on this. Okay. And what do we notice about this? Well, if y is anything but all zeros in each of these terms, and again, each of these terms is going to be 0, 1, 1, 1, 0, blah, 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 x, that's going to be an x, and it's going to go to a y. That's what these symbols here mean, which is another 0, 0, 1, 1, 1, 1, 0, 0, 0, dot, 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 n. There's going to be n terms for each, right? And this is a FOIL term. It's like a term from this algebra. Now, unless y is uniformly 0, these terms, this entire thing is going to zero out, this whole sum. That's going to be the case because this is a 0 indexed odd sum. There's an odd number of terms in a 0 index, so it's even. And if there's ones here uh, and not all zeros here, then this is going to alternate signs. +1, -1, +1, -1. And since it's even, they're going to all zero out. So unless we have all zeros on the y front, every single combination will zero out. You can verify this for yourself. It's simply empirically the case. So what we need to happen here is y to be 0 to the n. Otherwise, this will zero out. There's a zero probability. Again, this is if f of x is a constant function. So if we measure and we get that y is in this state here, we know that f of x is a constant function. F of x is constant. If we measure and we get anything else, then we know f of x is a balanced function. Because those are the only two possibilities. Balanced function. Okay, that's how it goes. If you guys have any questions, please post in the comments below or DM me. I hope you enjoyed this. And if you guys want to take a stab at the exercise I left, or if you want the solution for the exercise I left, I can LaTeX it up. Just absolutely let me know. I'll probably, after a couple of days, I'll LaTeX it up anyway. So, all right. Cheers, everyone.